Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is reduced voltage starters with timers. Our objective is to examine how timers can coordinate the orderly transition from start to run modes for several different types of reduced voltage starters. Obviously, this lecture operates under the assumption you've watched not only the reduced voltage starters, but also the timers lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time, pardon the pun, to do so now. For the most part, a majority of reduced voltage starters can be implemented with on-delay timers. However, when we examine soft starters, we'll additionally be making use of off-delay timers. The classic application example of on-delay or delay-on-energized timers is scenarios in which one or more contactors must open or close a measurable time period after some controlling input has been asserted. Let's first consider a primary resistor reduced voltage starter. You'll recall that a primary resistor reduced voltage starter starts a motor with resistors intended to carry primary current in series with the motor, and after a modified acceleration period in which inrush current and starting torque is comparatively less than a full voltage starter, the primary resistors are bypassed by the closure of the R or run contactor, and the motor is connected to full voltage. In contrast to the operator and rotational speed initiated transitions discussed in the primary resistor reduced voltage starters lecture, the transition from start to run mode can also be time-based. Let's walk through the ladder logic diagram of one such implementation making use of an on-delay or delay-on-energized timer. Note the inclusion of timer relay coil TR1 in rung 2 and the normally open time closure TR1A contact in rung 3. Let's say the timer delay is set to 2 seconds. This means contact TR1A executing the on-delay function closes 2 seconds after the timer coil TR1 is energized. An operator presses start, which energizes the S or start contactor coil and the coil of timer relay TR1. The contacts associated with the S contactor coil immediately change states. The S1 auxiliary contact closes and establishes a holding circuit, allowing an operator to release the start push button. The S primary contacts close, and the motor starts with reduced voltage given that the primary resistors are placed in series with the motor. The contacts associated with timer relay TR1, however, do not immediately change states, but only do so after a measurable time period, notably this timer's adjustable delay period of 2 seconds. Following a delay of 2 seconds, the normally open time-close contact TR1A closes, which energizes the R contactor coil. The primary R contacts close, and the primary resistors are bypassed. The motor experiences full voltage. Note the primary resistor reduced voltage starter method incorporating this timer exhibits a closed transition. The motor windings are never de-energized in the transition from start to run. When an operator presses and releases stop, the S, TR1, and R coils are de-energized and the associated contacts immediately return to their de-energized state. The primary S and R contacts open and the motor free spins to a halt. The timer relay resets, as does the entire system. With very little effort, we can employ the exact same technique for a part winding reduced voltage starter. Note the ladder logic diagram is essentially a repeat of the one used to control the primary resistor reduced voltage starter, with the exception of the series arrangement of the S and R overloads. Really only the primary schematic has changed significantly. You'll recall that a part winding reduced voltage starter starts a motor with only one set of windings with full voltage, and after a modified acceleration period in which inrush current and starting torque is comparatively less than a full voltage starter, another set of windings is brought in parallel, and all windings of the motor are connected to full voltage. Note that part winding reduced voltage starters are only applicable for 9 and 12 lead motors in the low voltage configuration. In contrast to the operator and rotational speed initiated transitions discussed in the part winding reduced voltage starters lecture, the transition from start to run mode can also be time-based. If you walk yourself through this ladder logic diagram, making use of an on-delay timer, you should find that the run contactor closes and brings the second set of windings in parallel only after a delay period after the start contactor is closed. Again, Note the inclusion of a timer relay coil, TR1, in rung 2, and the normally open time-closed TR1A contact in rung 3. Let's say the timer delay is again set to 2 seconds. This means contact TR1A, executing the on-delay function, closes 2 seconds after timer coil TR1 is energized. When an operator presses start, both the S and TR1 coil are energized. The contacts associated with the S contactor coil immediately change states. The S1 auxiliary holding contact closes and establishes a holding circuit, which allows an operator to release the start push button. The S primary contactor closes and brings one set of windings into play. The motor starts with reduced voltage. The normally open time-closed TR1A contact, however, does not immediately change states, but only does so after a measurable delay, in this case, 1-2 seconds. Via the now closed TR1A normally open time-closed contact, the coil of the R primary contactor is energized. Its associated contacts immediately change states and the R primary contactor closes. The second set of windings is brought into parallel and the motor transitions to full voltage run mode. If an operator pressed and released stop, the S, TR1, and R coils would be de-energized and their associated contacts would immediately return to their deactivated state. Both primary contacts open and the timer resets, as does the entire system. With only slightly more effort and complication, we can employ an on-delay timer for Y-start delta run reduced voltage starter. You recall that a Y-start delta run reduced voltage starter starts a fully customizable motor in a Y configuration with the windings experiencing only the comparatively smaller line to neutral voltage, and after a moderated acceleration period in which inrush current and starting torque is comparatively less than a full voltage starter, the Y configuration is broken and reconfigured in a delta, with each winding experiencing the comparatively higher line-to-line voltage. The Y-start delta run reduced voltage starter is only applicable for fully customizable motors like 6 and 12 lead motors, where both terminals of an individual winding are immediately accessible. In contrast to the operator and rotational speed initiated transitions discussed in the Y-start delta run reduced voltage starters lecture, the transition from start to run mode can also be time-based. Let's walk through the ladder logic diagram of one such implementation, making use of two contacts associated with an on-delay timer. Note the ladder logic diagram includes a timer relay coil, TR1, in rung 3, and both a normally closed time-open contact, TR1A, in rung 1, and normally open time-closed contact, TR1B, in rung 3. Let's say the timer delay is again set to 2 seconds. This means the normally closed time-open contact TR1A in rung 1 will open 2 seconds after the timer coil TR1 is energized. Additionally, this means the normally open time-closed contact TR1B closes 2 seconds after timer coil TR1 is energized. When an operator presses start, the Y, S, and TR1 coils are energized. When the Y contactor coil is energized, its associated contacts immediately change states. The Y1 electrical interlock opens, which prevents the simultaneous closure of the run contactor. The Y primary contacts close and place the three-phase AC motor in a Y configuration. When the S coil is energized, its associated contacts also immediately change states. The S1 auxiliary holding contact closes, which establishes a holding circuit, thereby allowing an operator to release the start button. The S2 electrical interlock closes, as does the primary start contactor. This motor experiences the comparatively less line-to-neutral voltage of a Y configuration and starts in reduced voltage mode. The contacts associated with the energized TR1 timer relay do not immediately change states, but only after a measurable delay of 1-2 seconds do they do so. The now open TR1A contact de-energizes the coil of the Y primary contactor, and the Y primary contactor associated contacts immediately return to their deactivated state. The Y1 electrical interlock closes, and the Y primary contacts open. The Y configuration has been broken with an open transition. Quasi-simultaneously, the TR1B contact closes, which serves to energize the R contactor coil. The R contactor coil's associated contacts immediately change states. The R2 electrical interlock opens, preventing the simultaneous closure of the Y and R contactor, and the R primary contactor closes, completing the transition to a delta configuration. The motor now experiences the comparatively higher line-to-line voltage of a full voltage delta configuration. When an operator presses and releases stop, the S, TR1, and R coils are de-energized, and their associated contacts immediately return to their deactivated states. Both primary contacts open, and the de-energized motor free spins to a halt. The timer relay resets, as does the entire system. Finally, let's consider soft starters making use of timers. You'll recall soft starters initiate conduction at a predetermined start voltage and smoothly ramp up to full voltage over an adjustable ramp-up time, T-up, for a soft start. During the run phase, full voltage is applied to the motor. Following loss of the input signal, soft starters can also smoothly ramp down voltage to 0 volts over an adjustable ramp down time, T down, for a soft stop. A timing diagram of the soft starter output and input signal might look something like this. Advanced soft starters and motor drives executing a soft start or soft stop function may also include additional contacts that give feedback about the state of the soft starter or motor drive and can be used to coordinate the timed activity of soft starts and soft stops. Consider a soft starter that has 3 associated contacts. 1. SS hold that asserts itself when the input signal is being asserted, as would a regular control relay. This one can be used for holding contact purposes. The 2 others execute time-based shifts. 1. SS run that only asserts itself when the soft starter is in the full voltage run mode, and another, SS active, that asserts itself whenever the soft starter is active, either in ramp up, full voltage run, or ramp down. When overlaid with each other on the timing diagram, they might look something like this. Note how the input signal relates to the 2 feedback signals, SS run and SS active. If you think about it, they're both in effect executing timer functions from the perspective of the input signal. Without explicitly stating it, SS run is executing the on delay function, and that only after a measurable period the input has been asserted does SS run transition to its opposite state, this time delay being the adjustable ramp up period, T up. The moment the controlling input disappears, SS run returns to its deactivated state. SS active, in contrast, is executing the off delay function. The moment the controlling input is asserted, SS active enters its activated state, however, maintains the activated state for a measurable period after the controlling input has disappeared. This time delay being the adjustable ramp down period, T down. Although not explicitly stated, SS run can be considered an on delay timer with respect to in, and SS active can be considered an off delay timer with respect to in. To further enhance the functionality, and admittedly complicate things, these contacts can also have normally closed and normally open sides. Let's examine a couple simple scenarios how this time-based feedback about a soft starter's run and active states can be used to coordinate a reduced voltage starter. First, let's examine a soft starter that needs to be bypassed in run mode. Soft starters have 2 important utilization categories. Soft starters categorized as AC53A soft starters are intended to indefinitely carry full primary current, and those categorized as AC53B soft starters must be bypassed after the soft start event and be given a chance to cool. Bypassing an AC53B rated soft starter with the use of an on-delay timer is essentially the repeat of the technique utilized in both the primary resistor and part winding reduced voltage starter method, with one minor exception. This time we're assuming the soft starter itself is capable of acting as a timer and generating the on-delay function. In this case, one of the normally open time-closed contacts associated with the SS run output. Although not explicitly drawn as a normally open time-closed contact, SS run is in fact executing the on-delay function. Given the soft starter itself is capable of generating this delayed transition, it frees this system from coordinating two independent devices, notably a separate timer relay with the soft starter. When employed in this ladder logic diagram and primary schematic, note that the R or run contactor should bypass the AC53B rated soft starter during the full voltage run period, yet allow the soft starter to do its thing during a ramp up or ramp down event. Let's walk through the ladder logic and see how this works. At startup, the soft starter receives power. Note soft starters, since they're solid state devices, ordinarily need to be constantly powered up to run. Note the placement of the e-stop and overload contact. When the e-stop and overload are in their normally closed state, the soft starter receives full pilot voltage and is powered up and ready for use. If either of these devices open, the soft starter would be completely depowered. This is critical to the functionality of the system during an emergency shutdown or overload event, which would disable the ramp down period and completely halt conduction. Additionally, note the placement of the manual motor starter immediately upstream of the soft starter serves to disconnect the soft starter from primary voltage for repair or troubleshooting purposes. When an operator presses start, the input signal is asserted. The soft starter immediately initiates conduction at the start voltage and initiates the ramp up time. The SS holding contact immediately changes states and establishes a holding circuit, which allows an operator to release the start push button. Note, however, the SS run contact executing the on-delay function does not immediately close, but only after a measurable delay period, notably the T-up ramp-up time. After this time period has elapsed, full voltage is applied to the motor, and the SS run contact closes. The R contactor coil is energized, and the R primary contactor closes, which bypasses the AC53B rated soft starter. Full voltage is applied to this motor, and the AC53B rated soft starter is given a chance to cool. When an operator presses and releases stop, SS hold and SS run immediately return to their deactivated state. However, the soft starter initiates the ramp down period, where voltage is progressively reduced from full voltage to 0 volts over the adjustable T down period. Note, when the R contactor coil is de-energized, the R primary contactor is opened, which allows the soft starter to conduct the deceleration period. After this time period has elapsed, the soft starter returns to a ready state. Again, note that the e-stop or overload would serve to completely depower the soft starter in the event the motor needed to be stopped during the soft stop event. Moving on, let's now consider an AC53A rated soft starter that does not need to be bypassed. However, it's making use of a friction brake. Recall from the reduced voltage starters with friction brakes lecture, available at the Big Bad Tech channel, I briefly introduced this functionality, so this might be a review. As previously mentioned, we're assuming the soft starter itself is capable of generating an output, SS active, that is asserted whenever the soft starter is active, either ramping up, applying full voltage, or ramping down. If you think about it, SS active is executing the off delay timer from the perspective of the controlling input, although it's not explicitly drawn this way in the ladder logic diagram. When employed in this ladder logic diagram and primary schematic, note that the friction brake should be removed the moment the soft starter initiates conduction and remain removed until the soft starter halts conduction. Note the primary schematic incorporates a B primary contactor and brake coil above stream of the soft starter. When the B contactor coil is energized, the spring-set electrically released brake solenoid experiences full line-to-line voltage, and the friction brake would be disengaged. Let's walk through the ladder logic and see how this system works. At startup, the soft starter is completely powered by pilot level voltage. An operator presses the start button, which asserts the input signal. The associated contacts SS hold, SS active immediately change states, and the soft starter initiates conduction at the start voltage and the ramp up. The closure of the SS active contact energizes the B contactor coil. The B primary contacts close, which energizes the electrically released brake. The brake is disengaged, the moment the saw starter initiates the ramp-up time. Given a holding circuit has been established by SS hold, an operator can release the start push button. Once the ramp-up time has elapsed, full voltage is applied to this motor. If an operator presses and releases stop, the input signal disappears and the SS holding contact opens. However, the SS active contact executing the off-delay timer function remains closed, ensuring the brake remains disengaged while the saw starter executes the ramp down action. Voltage is progressively reduced from full voltage to 0 volts over the adjustable time period T down. Once this time period is elapsed, the saw starter halts conduction and SS active opens. The spring set friction brake is engaged and the motor is brought to a halt. Again, note that the e-stop and overload serve to completely depower the saw starter and serve to override the ramp down action, immediately depowering the motor. Alright, that's about it for reduced voltage starters with timers. In conclusion, this lecture took a brief look at timers used to coordinate the orderly transition from start to run mode for several different types of reduced voltage starting methods. We observed that the on-delay timer can be used to open or close one or more contactors a measurable time period after some input has been asserted. Additionally, we observed that the off-delay timer can be used to keep one or more contactors opened or closed a measurable time period after a controlling input has disappeared. By no means are these the only suitable applications of timers and timing functions. However, they are extremely common and useful applications. We'll examine other applications and other timing functions in later lectures. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.